very much. This work has been carried out together with Sylva Emelin and Irina Hadi, who will heard her presentations, you know her. It's been carried out at Lund University in Sweden. The objective of this work has been to study the sensitivity of small defects in nano-sized FCC single crystal copper beams. And we have looked at two different crystallographic directions to see how that will influence the result. We have also looked at three different geometries. One geometry where we have a solid beam without any defects, and then we have looked at two different types of defects, an edge defect and a void in the center of the beam. We've also looked at three different cross-section sizes to see how the size of the beams will influence the results. And the results that we have compared are the strain at plastic initiation, the strain at final rupture of the beams, and also the strain at closure, because in some cases these defects will close entirely. We will also look at the plastic development and final rupture in detail to see the mechanisms behind this phenomena. So these are the configurations of the beams. So this is the solid beam. It's a rectangular beam. It has an length L and side S of the square cross section. Then we have a beam with an edge crack-like defect, like this, and the last configuration is through the thickness void. And as I mentioned, we looked at two different orientations of the crystals. They're listed here. I will call these orientations the 100 and the 1110. The 110, because this is the loading directions of the beam. We load the beams in the X direction. To solve the system, we have used the molecular dynamics simulations. We have used the freeware that's called LAMPS. And from this we can calculate the force of the atoms as the gradient of the potential energy. Then we get the acceleration of the atoms. We can time integrate and get the velocities and positions. And to do this we have used the EM potential. Eileen already talked about that, so I don't have to mention that again. And to time integrate this we have used a canonical ensemble called NVT ensemble, so we have a constant temperature in these simulations. So this is just a very simple description on how we do such a simulation. We start with some geometrical setup, so we place all the atoms in the beam. Then we relax the beam, so we find the correct starting positions of all the atoms. Then we fix the atoms at the ends of the beams, so they can't move anymore. So this mimics clamped ends. And then we apply constant velocities to these fixed atoms at the end. And we apply a positive velocity in one direction and negative on the other, so we stretch the beam. And then we displace these atoms at the ends until we get final rupture. And during this elongation we calculate a number of things, such as the lattice disorder, so we can find the introduction of plasticity, we calculate the positions and the forces and so on. So these are just some parameters that are used in the simulations. I will not talk about all of them, but we can see the beam length here is equal to 100 unit cells. We have the cross-section sizes 6, 12 and 18, so it's quite small beams, and also the defect size in the cases where we have a defect. It's 1 unit cell of width and S divided by 3 in height, where S is the size of the cross-section. So to be able to see when we get plasticity in these beams, we have to have some kind of parameter to calculate them. We have used the center symmetry parameter here. It's a measure of the lattice disorder of the material. So it basically calculates it at the point. Sorry. That's the one here. A summation of the distance between the nearest neighbors. So if this value is equal to 0, we have a perfect FCC material. But when we get some kind of other structures, this value will increase. And here we see a table with the typical values of different types of structures. We have dislocations, stacking faults, and also the highest values here are when we are at the edge or corner atoms. And this is because in these cases there are missing atoms. So that's why we get a very high value. So by using this parameter we can identify the different structures. So now to the results from these simulations. They're all summarized in this picture, basically. So here we have the strain at plastic initiation. That's with the index I. We have the strain at final rupture with the index F. And for some cases we will have closure of the defects. Then we have an index C here. And these are for the two different directions, the 1, 0, 0 and the 1, 1, 0. So if we start by comparing the strain at plastic initiation, these three curves, the green one is for the solid beam without any defects, the red one here is for the void, and the blue one is when we have an edge defect. And we can clearly see here that we have almost no dependence of the cross-section size. We have a relatively constant value of this strain at plastic initiation. We can also see that the strain is highest for the solid beam, as we would expect, and the lowest with an edge defect, with a void defect in the middle. If we now compare that in the 1, 0, 0 direction with the results from the 1, 1, 0 instead, we see the same trend here. The curves are in the same order, but we get lower values of the strain. And this has to do that in this direction we have a higher stiffness, so therefore we get the lower strain. So that was the plastic initiation. If we now look at the strain at rupture instead, we see that we get much higher values. In some cases we are almost at 60% elongation of the beams before we get final rupture. And we have no such clear trends about if a void or an edge crack is worst. But we can see in all cases the solid beams can take the largest strains. And then we have the last result here, which is the closure strain. And that's basically just 2 points, because this is just for the smallest beams that this will occur. This point and this point. So for the smallest beams and with a void, we can see that first we will have plastic initiation, then closure of the voids, and then eventually rupture. So now to understand what really happens in the beams, I will first show a short video, and hopefully this one will work. And then we will look at some snapshots from this video to see what happens. So if you can, there should be a play button down here. Yes. So first you see just elastic elongation. Then you have massive plasticity with lots of slip planes that are activated. Then you get multiple necking at 2 positions, and finally one of the necks will go to failure. And the color coding here is this central symmetry parameter that we see. Now we're going to look at some snapshots from this video, because that was quite fast, I think. So this is after relaxation. Then we have a constant. All the atoms have the same value of this central symmetry. Then this is the onset of plasticity. We can see that there are some slip planes that are activated here. This is close packed 1-1-1 planes that we see. If we increase strain even further, we can see that we form 2 necks almost simultaneously. One here at the end and one bit more in the middle. And then when we continue to load the beam, eventually one of these necks will grow to failure. Now, in the next slide, I want to compare the different directions instead. So here we want to compare the 1-0-0 direction with the 1-1-0 and see how they differ. And also we instead look at the case of a wrong button again. With an edge instead. And there we can see, when we increase the strain, the plasticity is much more local at the defect. It's not spread out over the entire beam, as we saw in this picture. And this can explain that we get much lower strain at plastic initiation and strain at failure, because it's much more local at the defect. And also here we can see it's the 1-1-1 planes that slip occurs along. And now if we compare those figures with the ones in the other direction, we get a similar trend. Also in this case, the plasticity is very local at the defect, but we get a different deformation pattern. Here we see the slip plane activated is this plane instead. And this is also a 1-1-1 plane. But since we have rotated the crystal, the 111 planes are in different direction as compared to the loading direction in this and this figure. So that's why we get these different patterns. So the last slide is for beams with a void instead. So this is the case for the smallest beams, and that's for the intermediate beam. And this is for the 100 direction only. And here we can see that also in this case the plasticity starts at the void, but it's somewhat more spread out over the beam than in the case of an edge crack. And that can explain these, go back, that this curve is in the middle, in between the edge and the solid one. And for these smallest beams, we can see in the next figure here that the void has completely closed. And as it closes, we form a void at this position, and we will quite soon go to failure at low strains. For the larger beam instead, this one, we can see that we don't get the closure of the void. Instead, it elongates, and we form two ligaments like this. And eventually, one of the ligaments will break, and then the other one will soon also break. And we can see that this beam can withstand much, much higher strains than the small one. So the conclusions of this work is that when we introduce a defect, we lower the strain for both plastic initiation and for rupture. Strain at initiation was almost independent of cross-section size for all the different type of beams. If we have voids in the beams, plasticity will induce later than an edge defect. So edge defect seems to be the worst kind of defects. We also saw large variations due to the crystallographic orientation, both in failure strains, strain at elastic initiation, and also the deformation pattern. And if we have beams with voids, we in some cases can have void closure, but that was only seen for the smallest beams and smallest voids. Thank you.